Hello and welcome to NPTEL MOOC on fiber optic communication systems and techniques. In this module, we will continue the discussion of coherent receivers. Just to recap, this is a direct detection receiver or simple intensity detector. Okay, you can detect intensity by putting up a photodetector and then have a load resistor and look at the current that is produced by the photodetector. No phase information will be detected using this simple system. On the other hand, this upper part is what you have already seen, right. So, this is the coherent homodyne receiver, because I am assuming the local oscillator frequency is exactly tuned to the signal frequency, that is incoming signal frequency, and this arrangement gives me the in phase component. But I know that I usually do not have only the in phase component. My received signals will actually be a complex signal in this fashion. So, I need to have both cos phi of t and sin phi of t to be available, so that I can add these two to essentially obtain the complex phase that I have transmitted. Okay. Of course, in the cases of BPSK that we have seen, the sin phi of t did not enter into our considerations because we had constellations which was just lying on the in phase axis. However, in other constellations or other modulations such as QPSK or M-Array PSK or quadrature amplitude modulation, you will have constellation points containing both the in phase and quadrature component. So, in that case, you want to be able to obtain the quadrature component as well. How do you do that? This arrangement is quite simple. You take the incoming signal ES, you take one part of that, let that part come to this other scheme, which is essentially the same as the top one. The difference between the top and the bottom ones with respect to this line here is that there is a extra phase modulator to which the local oscillator signal is used, so that the signal that comes out at this point will be JELO of t. So, this J stands for a pi by 2 phase shift, and using this phase modulator and biasing the phase modulator at pi by 2 gives me a phase or phase shift of 90 degrees, which in the complex form I capture it by writing this as JELO of t. Please note here that this would still be ES of t, and the two electric fields that you are going to get in the two branches would be ES of t plus JELO of t, okay, and the electric field that you are going to get here will be the difference between ES, the incoming signal ES and this ELO of t. So, there will be JELO of t. So, you can see that you have on one, so there will also be 1 by root 2 here, 1 by root 2, and I will now leave it as an exercise for you to get the photocurrent here generated on this top photodiode and the photocurrent that is generated here, and then take the difference between the two. When you take the difference between the two, you will actually see that the output will be something like square root PS. So, there will be a 2, or maybe there will not be a 2 because you have to mind whatever this half part is there. So, I will just simply write this as proportional. So, proportional to PS PLO, whose amplitudes I am again assuming to be constant, and now I will have sin of phi of t, right. For the case where I am going to perform BPSK, but I am going to perform BPSK on the phi 2 axis, this phi of t could be 0 phase or pi phase, okay, on this axis. So, I am actually going to get, or rather pi by 2 and 3 pi by 2. So, I am going to get either sin pi by 2, which is positive, or sin minus pi by 2, which is actually negative. So, I can actually obtain these two again by looking at the sign of what I am actually receiving. Now, when I combine that with this constellation, right, because on this branch, the in phase branch, this is the quadrature branch, I can distinguish the in phase signal phase or the phase of the incoming signal on the in phase axis by looking at the sign of I in, and I can distinguish the phase of the signals on the quadrature axis by looking at the sign of the current IQ, and in this way I can actually distinguish any phase that I would actually receive. So, for example, if my received signal happens to be this particular constellation point, okay, in this case the in phase component would be positive, the quadrature component would also be positive, and I would actually look at the signs of I in and IQ to make that decision. Okay. So, what I want to tell you is that this arrangement can give us full information about the complex envelope of the transmitted signal, okay, depending on what value of phi of t you have. So this is for the quadrature component, but for the in phase component, this output would be, photocurrent would be square root ps PLO cosine phi of t, where phi of t is the phase of the input transmitted signal. I am assuming that theta LO is equal to 0, or I can use this theta LO simply as a reference. And this detector scheme which I have sketched, which involves two different couplers, or in fact more couplers, but there is a extra phase modulator to induce a 90-degree phase shift, is called as a phase diversity receiver. This is diversity because there are two branches out there, and these two branches are receiving two different signals in the form of two different phases, and therefore this is called as phase diversity receiver, or sometimes called as IQ receiver. Okay, this is how you detect phase in optical domain. So if this entire slide can be written as detection of phase, or I should actually use the proper word, instead of detection I should call this as measuring of the phase, or measurement of the phase of the optical signal. Now why is this considered to be quite an achievement? Because this is considered to be quite an achievement over the last 15 years, is simply because earlier if you had to recover the phase, what you should have done is to let the incoming signal, okay, and then have a VCO or a local oscillator here. So you of course had to first put in the photodetector. You have the photodetector output driving the local oscillator, or rather the local oscillator would be generating something. The phase detector photocurrent after filtering would have driven the local oscillator, and the output of the local oscillator would again become combined again with the incoming signal Es of t, and then detected and then did all these things. Okay, this arrangement, which I have not really sketched it out here correctly, is called as optical phase locked loop. So this is optical because this is being done using lasers. So this is a phase locked loop, which is a very common device in RF systems. You can actually get very nice PLLs, very high performance PLLs with very narrow bandwidths, and in fact you can use these PLLs to synthesize whatever the frequencies that you want. Unfortunately, in optical phase locked loop, the major problem is that you are actually dealing with two different lasers. Okay, you are dealing with two different lasers. One of them happens to be at a remote site. This is a transmit laser, and then you have this one as the local oscillator here, right? So this is at the receiver side, but then you are trying to synchronize, you are trying to make this as a master laser and then this one as a slave laser by somehow putting this OPLL in the picture. So OPLL, what is it is supposed to do is to take the signal from the master local or the master laser and then tune the local oscillator such that the local oscillator would then track with the same frequency as the transmitter frequency, having a fixed phase difference from the transmit phase theta 0 and theta LO, LO being the local oscillator phase. But it turns out that this problem is actually very hard to solve for various reasons. For example, two lasers, when you try to match them or when you try to make them into a master and slave, can start producing what is called as chaos. Okay, and that is actually a big problem because that means any small change in one of the setting that you are going to use will result in an extremely large and unpredictable change called as chaos. Okay, so in fact this arrangement of using two lasers is used to produce chaos because two lasers, getting them to lock each other is an extremely difficult problem, and this is precisely the reason why, even though coherent detection was shown to perform much better than direct detection system that we discussed in the previous modules, okay, it was not really taken up as a viable option until about 2004 or 2005, when people decided, instead of working with an analog OPLL system, we will let the signal come in as it is. You have your coherent receiver, you generate the in phase and the quadrature components. I am showing a single coherent receiver, but this is a phase diversity receiver, of course. So this coherent receiver of course also takes in ELO. I am going to stop tuning ELO with ES, but what are the problems that I could have? Well, omega LO may not be exactly equal to omega 0. This problem is known as the frequency offset problem. Theta LO minus theta 0 might not exactly be constant, but it would actually be kind of a noise, and this noise actually has a physical reason why it comes out, because what is called as phase noise. We will study phase noise in the next module or in the end of this module. This phase noise is going to cause the phase of the signals to drift in a random manner. Okay. So, this is the phase noise problem, which we will call as PN. It may also happen that the transmitter may be X polarized, while the local oscillator may exactly not be X polarized, but it may not be exactly Y polarized also. It may lie at some polarization and you want to tune the polarization, right. So, this is the polarization problem, which can also be, so all these problems that exist because of not being or not implementing the optical phase lock loop will be handled by a block known as digital signal processing. There have been various algorithms that people have used in the wireless domain or in the traditional digital communication domain to address the problems of frequency offset, phase noise, and not exactly polarization, but similar to polarization. People have worked on it, and what more, you can actually have an adaptive procedure using this DSP. So, you can actually look at the samples that you are generating. So, these samples are the input to the DSP, and then you can tune the parameters in the digital domain such that you can make FO equal to 0, you can estimate precisely what is PN and compensate for the phase noise, and then you can correct for whatever the polarization crosstalk that these two would have endured. So, you can overcome these problems using DSPs. Granted that most of these DSPs are not real time, they are what is called as quasi real time, but in principle using these DSP algorithms you do not have to implement optical phase lock loops, and this is actually a big achievement in fiber optic communications over the last 10 or 15 years. So, this is a very important development, and this important development has made it possible for us to reach data rates which are about 100 gigabits per second and beyond. Okay. We will look at some algorithms for frequency offset, phase noise and polarization tracking in the later modules, but at this or in this module what we want to do is to basically look at our signal space analysis and to bring out a simple comparison between on-off keying and coherent receiver for a BPSK system. Please remember that this comparison actually is a very simplistic comparison in the sense that lot of choices that you need to make between direct detection receiver and coherent receiver are not going to be covered. For example, coherent receiver requires more optical components, and these optical components require their own power and their own stabilization. So, it will consume more power compared to a simple direct detection receiver. So, in cases where absolutely power considerations are maximum or power considerations are important, you would tend to prefer a direct detection system with the loss of spectral efficiency over a more complicated coherent receiver. On the other hand, if performance is the main goal and you do not care about the cost, then you do not normally use the direct detection receiver, but you use this coherent receiver. So, the choices actually depend on the application that is there, but purely from the performance point of view, performance meaning if you send in the same transmit power, which of the two constellations will perform better can be answered by looking at little more detail onto this constellation itself. So, for the BPSK constellation or for the on-off keying constellation that we will consider first, you have two symbols which are say 0 and 1. So, these are the symbols that I have transmitted. For 0 you transmit nothing, and for 1 you transmit some power. In terms of the constellation, this is sitting at 0 and this one is at square root of ES. Please note that as I have told you many times, I could have used PS also, but I am sticking with the energy considerations here because that is more common in traditional digital communication literature. Okay. Now what? Well, we have in a photo detector, if I am going to look at the photo current, whether I transmit 0 or I transmit 1, or whether I receive 0 or whether I receive 1, this photo current would actually be proportional to, or rather this would also include, in addition to the signal component, it would also include the noise component, and we have seen what different types of noises are going to affect our system. We will assume that it is the thermal noise that is prominent in this case, or if I am going to actually put in a preamplifier to overcome whatever the losses that the signal has actually experienced, then the noise that would be mainly for us would be the short noise. Okay. Turns out that short noise actually is not exactly having a Gaussian characteristic. So it will be little difficult for us to assume that or compare the performance with the short noise, because short noise is dependent on the signal power. But what we will do is to approximate this short noise as a Gaussian noise, or we will work with the thermal noise itself. Okay, so this thermal noise will be more or less Gaussian, although it is not exactly correct. But if you take this thermal noise as an approximation to what you are actually receiving, the photocurrents that you would receive will now be distributed around these points, right? And we have seen how to evaluate the bit error rate. This is the threshold that I have taken. This would be the error that you are going to make when you transmit bit 0, but incorrectly assume that this is bit 1, and this would be the error that you would make when you take that the bit as 0, but actually you have transmitted bit 1. Okay. Now this is simple one dimensional thing that I am actually looking at, and if I go back to this idea of the signal space concepts that we talked about, in that signal space concept what we actually had, so these are the noises, I am just for a moment removing the noises, but now this is my constellation point, right. So this is my constellation point here, the two constellation points at 0 and square root e. So I will relabel this one, so this is square root e, so this is, I am going to make this as 0 and square root es. So this is what I have, right, and I am assuming that the noise is Gaussian. So please keep this in mind and take it for now that this is actually operated under the thermal noise limit, although we know that when you have a preamplifier noise, when you have a preamplifier or when the power itself is considered, then the major noise sources are short noise and the signal spontaneous beating noise. But for now we will assume that this is all Gaussian noise, right. So I have a bit 0 and bit 1. I will make an error. So what is the probability of error? The probability of error will be the error in thinking that I have actually received a 0, but when I have transmitted a 1, times probability of sending a 1 itself, plus probability of thinking that I have actually received a 0 or received a 1 when I have transmitted a bit 0, multiplied by the probability of sending a bit 0 itself, right. So this is what I have. Now if I assume that my received signal R will be signal Si plus n, where Si could be either S0 or S1, and n is a thermal noise or Gaussian thermal noise with a Gaussian distribution. So assume that this is a Gaussian distribution. So I will write this as Gauss of 0 mean, but a variance of say sigma n square. Okay. Then what I have here, and please note that I am also going to call this distance between the two as d, right. When will I make an error? Suppose your received waveform happens to be this one, right. Clearly you would have transmitted 1, let us say, and then the received signal has fallen at this point. Okay. So this is my received signal. This extra amplitude must have come from noise, right, and if this noise is going to add only positive contribution to this, when I transmit a bit S1 or symbol S1, then there is no problem. I can keep adding the positive noise, and if I am now looking at whatever is the closest point to R1, the closest point would always be equal to S1 over S0, right. So when I have noise which is positive, it would always be positive and it would be in this particular manner. But when n starts to become negative, suppose I receive a signal R1 or R2 here, then clearly even if I have transmitted 1, the noise became negative and it actually is starting to pull the received points closer towards S0. If the noise reduces below minus d by 2, if noise reduces below minus d by 2, then it would move the received points onto this region. In this region, all the points are actually closer to S0, and therefore we will actually end up making an error of the kind this one, right. So you might have transmitted 1, but you would have received a 0 when n becomes less than minus d by 2. Alternatively, for this particular case, noise can be negative, doesn't matter, but when noise becomes greater than d by 2, then you are in trouble, because S0 might be transmitted, but it would actually put it into this region, and in this region all points are actually closer to S1 rather than to S0. So the condition for making the error, say P1 given 0, seems to be that the probability of noise being greater than d by 2. And what is the probability of noise being greater than 2? N itself is given by, or rather this probability can actually be evaluated assuming that we already had a Gaussian distribution for the noise. So, this would be integral d by 2 to infinity e to the power minus n square divided by 2 sigma n square, there is a 1 by square root 2 pi sigma square d n. Okay. So, this corresponds to the probability that noise is greater than d by 2. And in terms of your q of x function that we already have seen in the previous modules, you can actually rewrite this probability of error or probability of n being greater than d by 2 as q of d by 2 sigma n. Okay. So, you can write this as q of d by 2 sigma n. Now, if you take this noise variance to be some n0 by 2, right, that is sigma n square equals n0 by 2, where n0 by 2 is the power spectral density of the noise, then sigma n will be equal to square root of n0 by 2. So, I can actually rewrite this one as q of d divided by square root of 2 n naught. Okay. I am assuming that the noise variance is the same whether you transmitted bit 0 or bit 1, although again go back to our assumed definition of Gaussianity. Okay. So, this is what I am actually looking at. So, this would be the probability of n greater than d by 2, which is given by this. Of course, I have only evaluated this error. If you assume p of 0 equals p of 1, then the errors are symmetric, and this would actually be equal to the total error that I am actually going to make. So, this is the probability, and multiplied by half plus the same quantity multiplied by or the same quantity again repeats, and therefore, this is the probability of error for this system in which the two symbols are separated by a distance d. Please note that the only assumption that we have made is that of the Gaussian noise distribution and having same variance whether you transmit bit 0 or bit 1 or symbol S0 or S1. Now, it becomes easier for us to evaluate the on off keying as well as the BPSK system. So, in the on off keying, what I have here will be symbol S0 and symbol S1. The distance between these 2 points is actually equal to square root of ES. Therefore, the error will be q of square root of ES divided by 2 n naught. Okay. I forgot to mention here that this kind of a condition can also come in when you have a coherent on off keying system, but usually coherent on off keying system is not used because this is more simplified structure rather than to use a coherent receiver for on off keying. It is possible to use coherent receiver for on off keying, works exactly in the same way that we have talked about, and in fact, the noises that you get with coherent on off keying actually approximates the Gaussian noise very much. Okay. So, that is the small information out there for you, but now we have looked at the on off keying system. Even if it is coherent on off keying, that is all right. This is the approximate expression that we are actually going to get. Okay. Now, let us go to coherent BPSK system. So, I have S0 and S1, and please note the way we have defined the systems in this case. You have square root ES as the constellation point minus square root ES as another constellation point. This should be familiar to you from the previous module. Now, the catch here is that the distance is now given by 2 times square root ES, and when you plug in to this expression of q of d by this one, what you will actually see is that the distance is now 2 square root ES, and here you have square root of 2 square root of n naught, right, which of course can be simplified by writing this as square root of 2s by n naught, and you can actually show that the square root of 2 factor translates to about 3 dB improvement in the performance system. Okay. So, this is the error that we actually make, and you can also clearly see that probability of error for the BPSK system will be lesser than the probability of error for the coherent on off keying or the simple on off keying system. Why it is so? Because this q function will actually give you the area under this particular curve, right, and if you compare the two arguments, the argument for the on off keying system is ES by 2 n naught. If you take the ratio of these two, you are going to get n naught divided by 2 ES. So, this ES cancels, n naught and n naught cancels, and the argument is actually 1 by 4. That is to say, on off keying corresponding x value is only 1 by 4th of on off keying or BPSK x value here. So, if this corresponds to on off keying, then BPSK would be 4 times larger, and therefore, that would correspond to this point, and clearly the area under this red curve will be much smaller than the area under the on off keying system. The ratio of these 2 points is about 1 by 4. So, BPSK is higher than the on off keying system. So, and this is the Gaussian distribution that we have drawn as a function of noise here. Okay. So, clearly BPSK systems are performing better than the on off keying system. You can extend this BPSK system into additional modulation schemes such as this one, which is called as 4 QAM, or you can also consider 4 different phases here, right. This is called as QPSK system. Sometimes this is also called as QPSK, so you have to be a little careful in exactly what is the terminology being used, but the probability of error calculations for these are slightly more complicated, but it can be shown that the probability of error for this constellation is the same as the probability of error for this constellation, because rotations do not change the probability of error. So, we are not going to prove all this, and we are not going to consider the probability of error calculations for these higher order modulation formats. I will leave this as exercises and in the assignments for you to work on it. What we want to do now is to actually look little more carefully about the noise that we talked about, namely the frequency offset, the phase noise, the polarization tracking. So, what kind of an algorithm can we use to remove polarization problems and all those things. We will do that starting in the next module. Thank you very much.